So the next talk in this session today will be given by Martin إلساسر from Germany. And Martin, although he is an electrical engineer by profession, but he really have a lot of interest in astronomy, and especially when one day he found there is a competition to sight the very thin crescent, and he accepted to take that challenge, and that has motivated him more as an amateur astronomer. And then he put a lot of effort, and he really managed to break some of the record that was set before. So he is using the latest technology in terms of CCD, image processing, and daily or daytime observation of the thin crescent. In his talk, he will tell us about these techniques and how can be used and in what situation. So please, Martin. طيب حديثنا أو الحديث القادم بيكون عن رصد الهلال باستخدام الكاميرات الإلكترونية، وهي عبارة عن كاميرات شبيهة بالموجودة في الكاميرات تستخدم حاليا لكن بحساسية عالية وبتقنيات علمية التحكم فيها بالتفصيل، بالإضافة إلى استخدام مرشحات ومعالجة الصور. معالجة الصور قد يكون فيها أقرب تصوير لها أنك تحذف الخلفية أو الضوضاء اللي حول القمر وتحاول تركب صور القمر واحدة تلو الأخرى حتى يظهر لك القمر النحيف. سيحدثنا عن ذلك مارتن إلساسر from Almania.
Okay, thank you. Good afternoon, ladies and gentlemen. My name is Martin Elsässer. I'm going to give a talk on observing the lunar crescent through electronic cameras. At first, of course, I also want to thank the organizers and sponsors of this conference for the opportunity and the occasion to be here and give a talk on this topic, and I hope it will be useful to our joint endeavors. Okay, short outline of what I'm going to talk about. First, I'm going to give a short introduction to electronic imaging, but only briefly because most of the members are already doing that with their standard cameras. Then I'm going to talk about contrast as the central issue of observing the difficult crescents, which are close to the sun. Then I'm going to go into some technical details on a telescope system which can do that, talking about the components this requires. Then I'm going to talk about the benefits and the advantages of this all of this imaging approach and some of the results achieved so far. And then I'm going to come to some, hopefully not too bold, conclusion and give an outlook of additional things that might be investigated in this regard. Okay. Electronic imaging is actually not that difficult. Most of you will have already done that. You have some kind of lens, you have some kind of camera. The lens captures the light from the thing you're looking at and projects that light as an image in a plane, and there you have your electronic sensor which captures that image. Nowadays, everybody has a camera inside a cell phone, so this is commonplace. When you're trying to capture the crescent, with an easy crescent that you can also see with the naked eye, you will take a few considerations into account, but this is all of this is the basic stuff we all know. Of course, you will prepare for your observation. You will know when and where to look for what. So you will want to know where and in what position will the crescent be. You should choose a good and safe location with clear view of the horizon. Standing right next to a busy street is not optimum because the next car is going to run you over. Of course, you're going to try to use a good quality camera. You should use a tripod to avoid shaking the camera while doing your images. You should take a whole series of images with different zoom settings so that you capture the whole twilight scene and the crescent itself. And it's also useful to capture foreground objects like a tree pole, a mountain or whatever in your images. First, because that makes the image more interesting, it makes it more beautiful, as some of our members regularly demonstrate, and also that's useful for comparison. I'm just going to give two examples of a few images. That's a very classical scene, a bright crescent with easy to see earth shine above a city skyline. The bright dot to the left of the crescent is actually Mercury. So this is a very easy image that actually everybody could have made. A tripod helps in order to not to shake your camera, but apart from that, it's easy. If you use somewhat a longer focal length, you get a larger magnification, and then you take a whole series of images, and then you can combine several of these images taken with about 1 minute of time between them, and you can demonstrate how the moon moves, rises above the horizon, and how the color of the moon apparently changes due to absorption in the atmosphere. So this kind of imaging is rather simple because you're imaging something that you can see with your naked eye, so it's not that difficult. Okay, the thing I actually want to talk about is imaging the more difficult crescents. And the main topic here, the main problem with that is visual contrast. What is contrast? Contrast is visual contrast. Contrast is simply the difference in brightness between the thing you're looking at and the background. And that's the problem with difficult or thin crescents, because difficult crescents hardly differ in their brightness from the background sky, and that's what makes them difficult. And that is the main, and so your task when trying to capture such difficult crescents is to resolve that contrast, to show the crescent despite this very low contrast. And as we all know, and from all our observing experience, the human eye simply has limitations when searching for such low contrast structures. Below a certain level, the human eye simply cannot detect it anymore, and that would be the point where you could start using imaging techniques to reach further and further down into the low contrast regions. Okay, just a short visual demonstration what low contrast can mean. I have 3 simulated images of the crescent on the horizon. The one on the left is very easy. The crescent is comparatively bright compared to the background sky. This one is still visible, and this one here, yes, there is one. It might be difficult for you to see here in this setting. And the crescent, so a crescent of this brightness compared to the background might start getting difficult to see visually. And low contrast is when this gets worse and worse and worse because of stuff being in between, because of clouds or haze, humidity, which lowers the contrast during your observation. So, what is the reason for low contrast? This was already mentioned. The moon simply reflects sunlight. That's why we see the crescent. But the light from the moon has to pass through our Earth's atmosphere, and while doing that, additional light from the sun, which is scattered in the atmosphere, is added to what you are trying to look. And that's where the low contrast comes from. So the number one cause of low contrast is simply unfavorable weather, haze, humidity, or simply the fact that you have to look through an atmosphere because you are not an astronaut. And the second reason for low contrast is simply the difficult geometry of a small crescent. The closer you get to the sun, the smaller, the thinner the crescent gets, and the fainter it gets in its brightness. And with this very low brightness, it has to compete against the bright glare of the sky, and that's where your low contrast comes from. But these issues can be addressed to a certain degree by the imaging approach. And I'm going to talk about that now. Okay, if you want to use a telescope in order to image such a low contrast crescent, the telescope or the complete system usually consists of several parts: camera, filters, telescope optics, telescope mount, baffles, and specialized software, or the usual stuff. And I'm going to go into all of these in more detail in order to give you some indications of what to use here. Okay, the camera is actually not that difficult. You would not use a standard point-and-click camera simply because it's the wrong tool. You would use a simple industrial video camera which provides a digital, non-compressed data stream. So this is simply a small metallic box with a CCD sensor at the front, and this is what you would use for your observation. So this is different from the cameras you normally use for imaging, and also it's not a professional astronomy cameras which are big and cooled and slow. This is something in between. Okay, also this camera would usually be a monochrome camera. Not a color camera, but a monochrome color to capture monochrome images, because that gives you the full sensitivity of your CCD chip, and that allows you to use filters in order to improve contrast. I'll show an example of that just right afterwards. Okay, these cameras usually have a fast frame rate, so that they provide you with a live view of what they're looking at. And this live view is useful because it's more realistic to look at. And also this fast frame rate gives you the ability to capture many images and then to add these images in order to reduce inherent noise in those images. The typical properties of such a camera would be it has a CCD chip, has something like 1 megapixel, delivers you 15 frames per second, and uses, for example, a USB 2 connection. That would be a standard tool for this kind of observation. Okay. The next part that is important are filters. Why do we use optical filters? Filters can be used in order to selectively reject colors in the light that arrives from the scene, and you would usually reject colors where the contrast is very low, because this makes it easier for you to see faint crescents. A typical example: if you're observing during daylight, then the sky is bright blue, and by removing that blue light, the crescent gets far easier to see because you remove the strong scattered blue light. On the other hand, if you use too strong filters, then that would increase your exposure times, and that would stop you from using fast frame rates. So you need some kind of compromise. The typical compromise is to use a dark red filter when you have some kind of observation where you have blue skies. So if the sky is still blue, you would use a dark red filter where you can still look through. It does not have to be infrared. We're not talking about, maybe I should make this clear. In the beginning, when I first described these observations, I said I'm using an infrared filter. And this confused people because they thought, you're using thermal radiation. You're not seeing a crescent. You're just seeing the moon as a glowing piece of rock. No, this is not true. The light we are using is only slightly redder than what we can see. Thermal radiation is far longer and something completely different. So we are not using thermal radiation. We use a red filter usually, and maybe some slightly more reddish light than our eye can usually see. Okay, so this is not thermal radiation. Okay, filters. Just as an example, what alone the filter can do for you. The image on the left was taken in daytime with a high magnification scope. Oh, wrong side. Okay. Was taken in daytime with a high magnification scope, and it shows the moon and the background sky. And we are using white light, so we have no filters. Everything the camera captures is being displayed. And you see, the moon is not much brighter than the background, so contrast is rather low. And just by adding a red filter on the right, you see that the background gets much darker. And so the contrast has massively increased simply by adding a small piece of reddish glass in front of your camera chip. So this is nothing evil or nothing incomprehensible. Just by using a simple red filter, you can massively improve contrast of the thing you are looking at, which simply simplifies matters for you. If you have blue skies, if you have whitish skies, then the filter probably will not be able to help you anymore. Okay, so the next part you need, of course, are telescoped optics. You should look for an optics which delivers you good contrast and color correction. You should choose a rather small optics, actually, because the focal length of the optics should fit your camera sensor, because you want to capture the full crescent at once. You don't want to see parts of it. You want to capture the full crescent, the full extent of the crescent. So your optics is actually not too large. But on the same time, it must not be too small, because if the diameter is too small, you might not be able to get the resolution you need in order to capture a very thin crescent. So you're somewhere in between. I have used small optics with a diameter of about 100 millimeters to good effect, and there are a large number of good enough optics in that range. So the optics is not that critical. You have a wide range of choices if you choose a sufficient quality. Okay, the telescope mount, another very important part. The telescope mount is to point the telescope and camera system at the moon and then to track it automatically. And with a modern telescope mount, with go-to capability, if it's properly aligned and properly set up, you don't need to be able to see the moon with your eyes anymore. If the whole system is properly set up, just by pressing the correct buttons, it will point towards the moon and it will follow it correctly. There are several mounts available now today which can do that for you. So there's no need to search for the crescent. You can have the telescope point at the correct location. The further up in the sky you are, the easier it is, actually. Okay, when choosing a mount, you should take into account that the strength and sturdiness of this mount is not only determined by the weight and length of the optics, but also of the baffles you might use. But this is not critical. There are several different mounts available, more than a dozen actually, who are strong enough to do this for you, even if you have to use a long baffle system. Okay, baffle system, what do I mean with that? Baffles. Why would we use battles? Not battles. Baffles with an F. Okay. When you as Jim already mentioned, when you're trying to observe crescents in the evening, and if you're trying to observe difficult crescents, you might start observation during daytime. And then you have the problem that you have the very bright sun very near to your field of view. And that is a serious danger to your equipment. So you should make sure that no light from the sun hits your optics in order to prevent a dangerous heat build-up inside of your telescope. That is a very important issue. If you get that wrong, very wrong, you might have a fire inside your telescope. You don't want that. If you actually try to observe with your naked eye, you could actually lose your eyesight if you do that wrong. So just like driving, you should do it correctly. Don't get on the other lane. Do it properly. Okay, that's why you use baffles. So the baffles are tasked in order to prevent the light of the sun from hitting your optics. And if you try to get really close to the sun for sports reasons or something, then your baffle system can actually be quite long, several meters in length actually. And so this can place a very serious load on the telescope mount, which has to hold and drive this system. Okay, as an example how all of this might look, this is a complete setup of a rather big system. You have actually the small optics down here. This is this big and sturdy telescope mount, and you have 3 meters of baffle in front of this just to hold this small piece of black cardboard which casts a shadow on the optics. So the only purpose of all of this mechanics in between is to have this piece up here which casts the shadow on the optics so that the sunlight does not enter the optics. You could do this with a person holding the cardboard up by your hand, but that's not really convenient for the person. So you use some kind of mechanical thing to hold this baffle system for you. Okay. The baffle system gets the longer, the closer you want to get. So 10 degrees is really simple. You hardly need the baffle at all. 5 degrees already requires a good baffle. And if we're talking about 3 degrees, it will get several meters long and will be quite a massive effort. Okay, camera software. This is actually the most important single part. Because what you're doing with imaging, you're looking with your naked eye, you're looking at the result of the camera which is displayed on your screen. So the software which drives this camera is a very important part. What does the camera software have to do? Of course, it has to control all the camera settings, exposure, resolution, frame rate, and so on. The camera software displays the stream of images you get. It stores those images and all the data you capture as a documentation. And of course, with the proper software, you could immediately share this image with any number of other viewers. I think Kamar is going to talk on this topic later. So the camera software is a very important component. Not just because it drives the camera, but because the camera software allows you to do far more. Okay, if you have a low contrast crescent, of course, the data captured by the camera also has low contrast. But what you can do with proper software, with a specialized software, you can tell the software in real time, please increase contrast in the data you have captured and show me an increased contrast image. And that's the most powerful component of the overall system, because this approach drastically improves the visibility of low contrast structures in real time. You don't have to spend 10 minutes on image processing and then return with a single image. You can do that in real time. And a large part of the overall performance of the system comes from the software, actually. I will try to give an example of this. This was an observation I did last year. It was early in the morning. The sun had just risen, and it was a few days after full moon. So there should have been an almost full moon in the sky. The sky was so hazy that I could only see the trees on the next mountain range, but I couldn't see anything of the moon, despite it being almost full moon. Okay, so I took this image with a standard camera, and I looked at the image, and I couldn't see anything. Okay, then I did some standard image processing, and what a triumph, this appeared. Inside the circle, this would be what you get when you try to do image processing with a standard camera image. So this was a good occasion to test all of this imaging system. Okay, so I attached... Can you see that? Is there something? Okay, so now I attached a small telescope, a simple red filter, and the camera system to the computer, and this is the raw image I got. So yes, there is something to be seen, but it's not really clear, because this is just standard raw data. Now we say, please, software, do us some contrast enhancement. And this is what you get. So if you simply press one button, do live contrast enhancement, you get this. Okay, now we have a lot of artifacts in the view, in the image. Actually, we have these bands up here, which are artifacts from the chip. We have these dust donuts, and we have a lot of noise because we did the contrast enhancement. But all of this can be compensated because you can actually capture so-called flat fields, which measure these effects, and then you can apply these flat fields again in real time to remove them. So if you do that, you get this, a much cleaner image. And now you can capture a lot of images in sequence because you have a high frame rate from your camera. And you can stack these images. This reduces much of the noise. And then you can even more contrast enhancement, and you get here. So this is the important comparison. This is the raw data captured by the camera. And by doing real-time live image processing on the thing, on this data, you get this view. And I think this is a very well visible comparison of the power simply of this live imaging enhancement. This is still a live image. You can have kids running around your telescope and holding their hands in front, and the image would get dark. So this is a live image, which makes it very easy for you to demonstrate this to other people. You could move the telescope around, and the crescent would move. So this is a very powerful demonstration of how important simply the software is in all this thing. Okay. So this is some of the technical details. Benefits and advantages. So simply the fact that you are imaging and storing the images and the data is a valuable documentation of your observation. You don't just have, yes, I saw something, but you have images and data to document your observation. So the credibility and the usefulness of this observation is improved. We could, for example, start measuring the contrast in these images to improve the existing visibility models simply by capturing and storing this data. Also, that's an important thing, imaging does not really depend on your personal eyesight or on your experience with telescopic viewing. That's what Jim mentioned earlier. When several people try to share a telescope, it's always a pain because everybody would have to focus for their own eyes on a difficult crescent, which might be difficult if you don't actually see something. And this is not a problem with imaging because people are looking at a TV screen effectively, and everybody I have met yet is really good at looking at a television screen. Everybody has the same experience on television, so this personal eyesight element is not that vital anymore when you do imaging. And of course, imaging easily scales to any number of participants. When we start broadcasting the images we get per television, you could have millions of people viewing this enhanced view. Okay, so imaging can compensate. By using this imaging technique, you can compensate for your weather problems to a certain degree. And of course also, when you are doing successful imaging, this demonstrates the correctness and precision of all these astronomical calculations, because all this is used. You're using these calculations to point your telescope, and if your calculations are wrong, you would point it at the wrong spot, and you wouldn't see anything. So when you succeed with imaging, you have demonstrated that all the steps you did, all the calculations were correct. That's also an additional useful feature of the imaging approach. Okay, so what results have we achieved so far? This imaging technique has proven quite reliable, actually, for the observation of low contrast crescents in daytime or in twilight, and simply beyond what the human eye can do. So this can be a certain equalizer for weather or experience. In terms of values, we have managed, several groups, I was one of them, have managed to image the lunar crescent at less than 4.6 degrees in distance. This was a daytime observation. And after sunset, I didn't have much occasion to do that yet, but I had one occasion earlier this year, and it was very easy to image the crescent at about 6.5 degrees on good but not perfect weather conditions. So, and another thing, by using this technique, we have repeatedly imaged the crescent at the moment of conjunction, slightly before, slightly after, or at the moment of conjunction. This shows that there is something to be seen at very small elongations, or at least there is something there. Whether you can see it is another issue, at very small elongations. So this is an example, just to show you one of these not so pretty pictures. This is an example of a very thin crescent we caught 1.5 years ago. This is actually a crescent at only 4.7 degrees elongation, imaged in bright daylight, so very near to the sun, and we still see a 90-degree arc of the crescent, which is actually seems to be broken into several pieces, because here apparently brighter parts of the lunar surface are reflecting the light, and here the lunar surface seems to be darker, but it still is a 90-degree arc, though we are well below the Danjon limit. So this is one of the practical examples. Okay, now for the conclusions. I think this imaging approach has demonstrated that conjunction itself is not really a magical moment. The view of the crescent does not change around conjunction radically. It's not something that's switched on or switched off. As several people have managed to image the moon just before, just after, or at the moment of conjunction. A word about the Danjon limit. The Danjon limit was usually thought to be a hard limit beyond which there would be no crescent visible at all. I think this has conclusively been proven wrong. I personally see the Danjon limit only as a rule of thumb for when visual observation really gets difficult, but by using imaging techniques, which can reach lower contrast, you can go far below this value. Where the limits of imaging might be is difficult. I think this depends largely on your weather conditions. The higher your mountain is, the better your weather is, the closer probably the lower contrast you will be able to do. And now for the bold statement at the end, I think by using the imaging approach, you could actually show the moon in one of its phases on almost any day of the year from a very good location. Because if we can go below 5 degrees, there are only a few days in the year where the moon throughout the whole day is at less than 5 degrees elongation. So by using this imaging approach, we could show it at almost any day of the year, in daytime probably, or at night, of course, it's simple, but almost any day of the year, it would be visible by using the imaging approach. So, as an outlook, maybe to remove some of the controversy, you don't have to decide whether imaging or not imaging. You can do both. You can do both at the same time. You can have a telescope doing imaging, and you can use that, when it shows you the crescent, to guide your visual observation, even if you don't use that result. But if the telescope shows you where the crescent is precisely, then that guides your eye and simplifies visual observation too. So visual observation can simply be a useful tool that also improves your abilities to visually see very faint or very thin crescents. And I think these crescent imaging techniques, just like photography in general, is spreading, and I hope it will be able to use this technique, and it will play a useful role, just as photography in general has been a great advancement to the science of astronomy when it was first started some 120 years ago. So I think those were my main points, and I think that was my presentation. Thank you.